All right, we're going to look at 7.2 star, and this section is on natural logarithms. So this should be kind of a review from college algebra. But the definition we're going to give is the calculus definition, and it goes like this. So let x be larger than 1. And here, again, the ln x is defined to be the integral from 1 to x, 1 over t dt, x greater than 0. And we'll show you that it will satisfy all the log properties. Well, if x is larger than 1, let's say, let's draw the 1 over x curve. This is 1 over x. And we go from 1, oh, sorry, let me say that's 1 over t. So this is the t-axis. Okay, so the graph of that is 1 over t, and we're going to go from 1 to x, and 1 over x, 1 over t dt, as long as the function is positive, that means above the x-axis, that is equal to the area under the curve from 1 to x. So we use the fundamental theorem of calculus, which has to do with taking the derivative of an integral. So we get the derivative of 1 over x, 1 over t dt is, oh, sorry, the derivative of ln x is the derivative of the integral 1 over x, 1 over t dt, and that's 1 over x. Remember, you just replace t with x when you take the derivative of an integral. So this shows us that the derivative of ln of x is 1 over x, and that's important. Let's go back and remember the log rules from algebra. Well, ln of a product is the natural log of x plus the natural log of y. You can separate them out and add. Ln of division changes to subtraction. Remember, a log is an exponent, so these are going to follow the exponent rules. When you multiply bases that have the same exponents, you add the exponents. When you divide things that have the same bases, then you subtract the exponents. And when you have a power, you can bring that down in front. So that power comes down in front. Okay, and the proofs of these are in the text, so I want you to look at these. Make sure you take a look at those. Okay, let's look at graphing the natural log function. Now, the first thing we note is that the derivative of ln of x is 1 over x, as long as x is greater than 0, and that means y prime is greater than 0, so y is increasing from the first derivative test. So remember, when the tangent lines are positive, the slopes are positive, so your function's increasing. So this is an increasing function. Let's check what it does at infinity. Limit ln x at infinity. Well, this is an increasing function, so as x goes to infinity, your y is increasing, so your function is going to increase, so this is going to go to infinity since ln x increases. It doesn't change direction. Okay, well let's look at some more limits. Limit x approaches positive infinity of 1 over t, and the ln of 1 over t is just a second. Let's look at this limit. Let's look at the limit. What happens as you go to the right of 0? So as you're coming in, here's your curve as you're coming in from 0 from the right. Let's see what happens to the graph. All right, we're going to change variables. So we're going to say x is 1 over t, and that means t is 1 over x, and as x goes to 0, that means t goes to infinity. So this limit changes to t approaches positive infinity, ln of 1 over t, but we can use the ln rules, and that's going to be the ln of 1 minus the ln of t. Division changes to subtraction. Well, ln of 1 at 0, so this is minus the limit t goes to infinity ln of t, but we saw right here from the graph that this limit is up here. We said that's infinity because ln of t is an increasing function, keeps increasing as t goes to infinity. So this goes to negative infinity because of the negative out in front. So this tells us that the limit as t approaches 0 from the right of ln of t is negative infinity. That's important when we graph it. Okay, let's check concavity. We take the derivative, the second derivative, so that's going to be negative x to the negative 2, which is negative 1 over x squared. And again, when x is greater than 0, y double prime is less than 0, it's negative, because of the negative sign, x squared is always positive. So this is going to be always negative for x greater than 0, so we have a concave down graph. When the second derivative is negative, it's concave down. And then we look at ln of 1, but according to the definition, that's the integral from 1 to 1, 1 over t dt, and we're not going anywhere, so that's 0. So we get the point 1, 0. So that gives us enough to graph this function. It's increasing concave down, and it goes to the point 1, 0. It goes to negative infinity here, so we have a vertical asymptote. On the y-axis, never gets there. It keeps going to negative infinity, and this goes to positive infinity. So graph, this is the graph of ln x. This is x axis. Okay, let's look at another definition. If you remember E E is like pi. It's an irrational number. That means it never ends, never repeats. E is the number such that ln E is 1. And you can determine by a lot of different methods that E is 2.718 and it never repeats and it never ends. So we say it's about 2.72. And like pi is like 3.14. Never repeats, never ends. It's irrational. Okay, let's get to the chain rule. Again, these are looking at definitions the calculus way. So the chain rule says that this derivative is 1 over the function times the derivative of the inside function, which is just the derivative in the numerator and the function in the denominator. So, for an example, here's an example of an integration. We do the integral tangent x. We want to integrate tangent. We change that to sine over cosine, definition of tangent. We use substitution. The derivative, we pick u to be cosine. Derivative of cosine is minus sine. Substituting back in, we have minus du is sine x dx. So this right here replaces this right here. And u is cosine, so that's just negative 1 over u du. Well, that's negative ln absolute value u plus c, which is negative. Okay, substituting back in for u, we get u is cosine x, and this is a indefinite integral, so we need the plus c. The negative can come up. Remember, any numbers in front can come up and become an exponent, and that's 1 over cosine, which is secant. So the integral of tangent is secant. Now, question is, where does that absolute value come from? So, what we have to remember is that the ln, the absolute value of u, is the integral of 1, let's just say 1 over t dt. Let's just say t here. Okay, so why is that? Well, remember the absolute value of t is defined to be t, if t is positive, negative t if t is less than 0. So, if t is positive, I'm sure you're able to see what's going on here. If t is negative, well, then let's say u is negative t, so then u is positive, and we're going to have the integral of 1 over t dt, which is the integral of 1 over negative u, negative du, and again, that's going to be the ln of u. Because du is negative dt, so we can substitute that in here. see, which is, let's see, that's ln u. So if u is greater than 0, that gives you t negative, and that gives you the same result. So we have the ln of the absolute value of t is the integral 1 over t dt, and that's why you need absolute value. It gives you the same result whether your variable is positive or negative. So look at exercises. I did some sample homework problems, 42, 56, 60, and 64 under the sample homework. All right, let's look at log differentiation. And let's look at this example. It's pretty complicated. The first step is to do the log of both sides. Well, remember, multiplication changes to addition. The exponent can come down in front. So again, we're making this more simple. Then we do implicit differentiation. And the derivative of log, or ln, is y prime over y. Actually, we should take the natural log of both sides here. Let me fix this, because the derivative is different for log. So we'll do ln, since that's what we've been talking about. And the derivative of ln of y is y prime over y. Implicitly, y is a function of x. The derivative of this is 3. The function goes on the bottom, and the derivative of the function goes in the numerator. The function goes in the bottom, and the derivative goes in the numerator. We multiply both sides by y. And then we replace y with the original function. I just factored out this 2 and put it with the 3 to get 6. And you can simplify it, but you don't need to. And that would be the final answer. So that's called log differentiation, and you can look at some of the examples I did in the example homework. Okay, so I hope this helps when you look at 7.2 on natural log.